Don't you start talking about the state of the hemisphere? Which of these?
Go on the first up the top and then 12Z.
I have no idea what they were. I think that's fine. All right. Welcome to Weather Watch. Greg is going to start. I think that's what the plan is.
Okay, welcome to Weather Watch. I'm going to start by showing the jet stream situation today. The transition to winter in the northern hemisphere is almost complete now. You can see that the polar night jet in the southern hemisphere down here, what you can see of it is mostly disappeared. It's kind of broken up and not much there. The subtropical jets in the southern hemisphere are pretty much disappearing now. This is part of one that's left. They're just little fragments of subtropical jets, nothing like there was before. If you remember before, a couple weeks ago, the subtropical jets in the southern hemisphere were connecting up with the polar night jet. Now there's no polar night jet, and also the subtropical jets are pretty much disappearing. That suggests that the Hadley circulation, if you think of it that way, is weakening toward the southern hemisphere and strengthening toward the northern hemisphere. And in the northern hemisphere, we have some substantial subtropical jet activity now. Back in the summer, the northern hemisphere looked like this with hardly any subtropical jets. Now we got a lot of them. We also have the big polar night jet at high elevations coming around here, and immediately as that happens, we're seeing the subtropical jets connecting up with the polar night jet here, and then they kind of go inside. The connections aren't full yet, but they're starting to make them. And when they connect, what I'm claiming is this touches off strong quasi-geostrophic circulations in the lower troposphere. So this is all starting now. You don't see the polar night jet going all the way around, except for a little bit here. It's the contouring interval I'm using. This is a 40 meter per second contouring interval. If I would go down to 35 meter per second, you would see this polar night jet connecting all the way around. Now, when these things start to happen, the tropical, extratropical circulations, by these things I mean these intersections, the tropical, extratropical circulations become much stronger. And so if you can go down to the precipitable water down here, the 12Z, look what's happening. You can see the jets kind of showing a little bit on there. But what you're seeing with the precipitable water, we'll go back one and get the frame just above that without the jets on it, right here. And what's interesting about this is look at these atmospheric rivers. Very strong atmospheric rivers going very far north now. And these atmospheric rivers are associated with those intersections when the subtropical jet plumes up and connects up with the polar night jet, or they intersect. That seems to be when you get really strong atmospheric rivers being pulled out of the tropics. At the same time, last time we looked at this, there were lots of atmospheric rivers in the southern hemisphere. They've almost completely disappeared, except for this. This is actually the IPCZ southern branch of it there. So the circulation is pretty much flipped, and now we're seeing much stronger pluming of the tropical air toward the pole. And I think that's enhanced or attracted by the polar night jet.
Okay, great.
So, go ahead.
It's not a question. Is there an objective way to define when these the subtropical and polar night jets are superposed? Do you have a way of defining that? So if someone wanted to do a calculation to see the latitudinal extent, polar extent of these atmospheric rivers, could they look at a correlation between?
Yeah, I think that's something we're actually trying to work at with Megan Chat. We haven't quite figured out how we're going to do this yet. What actually happens is as a subtropical jet, as the plume of upper level cold tropical air approaches the polar night jet builds downward. And what you see when you look at a cross section, the polar night jet is actually building downward and below the subtropical jet. As you're intersecting these air masses, the jet thermal wind that creates a jet just builds all the way down, and it starts to create a circulation in the lower troposphere from building all the way down. And then that circulation picks up the baroclinicity that's laying on the ground, the cold air that's laying on the ground in the polar regions, and picks it up, and then we start getting big polar surges. So I think this is the beginning of real winter now, when these things reach up there and you get that exchange with the surface air. So I think it has to be a fully three-dimensional type analysis to be able to do this, and I'm not sure exactly what you look at, because there's so many factors involved. But it's nice to look at these three-dimensional depictions of the jet stream, because you can see in 3 dimensions these intersections occurring. Or these, I don't know, maybe intersections is a bad word, because you're really looking at slipping a cold upper tropospheric air mass that's in the tropics. You're slipping it underneath the polar night jet is what you're doing. And that changes the thermal structure underneath, and that's why the jet builds downward. The jet is a result. It's not the cause, it's the result of these air masses intersecting. So I think this is a realization of what do you call it, the Lewis and Palm flux. We talk about the global circulations as having a Hadley cell in an axisymmetric sense, but then on top of that you have Lewis and Palm fluxes of heat and momentum toward the pole. These are Lewis and Palm fluxes, and they add up to create, over time on average, they create a Hadley circulation, which is from the ITCZ all the way to the pole. And so that's the interesting aspect of that. Well, I'll let you go on, please. Well, yeah.
What is DNVI on the scale?
Your scale over there, DNVI.
Oh, DNVI, density of the vapor integrated vertically. So it's the precipitable water.
Do you integrate from the surface all the way to the
All the way to
zero?
Yeah, the vapor, the total mass of the water.
Okay. Thanks, Greg. So next we're going to go to the radar image for over the United States. On the radar loop. And it's a pretty quiet day over much of the continental United States. Some light rain showers over the parts of central Texas. An area of precipitation that moving through the upper Midwest and into the Ohio and Pennsylvania this morning that caused a little bit of snow in the northern part of that, and I guess light rain and snow over parts of northern Ohio. The Weather Service, I think last night, was expecting for even the southern parts of Wisconsin to see maybe a slushy accumulation on roads, and they had just some statements about that, but I don't think that happened at all. At least I wasn't up at any point where I saw flakes falling today. So it's again, pretty quiet day over the U.S. Let's look at a satellite image. Which goes, look at the IR, please. Not the week long, but the shorter one. And you can see associated with some of that precipitation, these high clouds that are streaming off eastward. Note, as we could have mentioned this in other classes, that just because you have really deep you see high clouds here, doesn't mean there's deep or heavy precipitation necessarily falling. These high clouds in this IR image, they're colder cloud tops, so just cirrus. In some places you might have extreme deep convection occurring and heavy precipitation, but just having those colder cloud tops does not necessarily correlate with heavy precipitation at all times.
Those aren't particularly really cold, though, are they?
Right, yeah, they're just
They're colder in the ground.
colder in the ground, but they're not as
The yellows and the reds are really cold, yeah, that's
Right.
really high.
But your attention might focus on this, say, oh, there must be some heavy precipitation there, but that's not the
You
case.
could probably use that day cloud type image, I don't have the link here, but the one that has the weird colors on it would show you the higher versus lower clouds too.
Right. So, again, a very quiet pattern over the United States. You can see evidence of maybe sort of a cyclonic circulation over West Texas, affecting some of this water vapor northward. But really, just a rather pleasant, quiet pattern over the United States. If you look out over the Pacific, though, and we'll go to goes west, and look at the Pacific IR. The Terminator hasn't arrived yet. There, we have a really impressive stream of cloudiness from just north of the Hawaiian Islands all the way up toward British Columbia. A nice and perhaps developing atmospheric river or warm conveyor belt associated with it, with this plume of moisture that's again originating from deep in the tropics heading northward. Vigorous cyclonic circulation just north of the Hawaiian Islands, where we have really small cellular convection under very cold conditions in the middle troposphere, getting this deep convection. And it's of interest, this weather system is going to slowly slide southward toward the Hawaiian Islands, and they actually have blizzard warnings on the Big Island for up to 20 inches of snow, winds in excess of 100 miles an hour on the volcanic peaks in Hawaii over the next 12 hours or so, beginning of the next 12 hours or so, continuing into tomorrow. So as this front makes it to lower latitudes, they're expecting some really cold air, very top peaks, and significant snow, even in Hawaii. So if someone's vacationing in the islands here, it's going to become not the best weekend, miserable, chilly in the 60s, which is not too bad for us if we got 60-degree weather here, but for them it's going to be bad. But in the highest elevations, they're expecting significant snowfall. And you can see this, again, this kind of clouds descending anticyclonically to the west of this deep upper low, and helping to force that further to the south. So pretty active pattern in the Central Pacific. Jets aren't extending all the way across the Pacific. When you get these situations here, I think this might be the beginning of a period of a retracted jet over the Central Pacific, and you get these cutoffs forming in the Central Pacific. Let's go next.
That Hawaii thing is really interesting. Sorry to interrupt, Michael. There was a guy, when I graduated here, there was a guy in my class, Neil Oyama, who was from Hawaii, and I asked him about, the general weather there, and he said, overall, it never really varied by more than 5 or 10 degrees all year round. But he said if it got much below normal, they would put out an extra blanket warning so that people would know to put an extra blanket on when they went to bed. So I wonder if they're issuing an extra blanket warning for this one. Anyways.
So, that's the conditions out over the shore. Let's come back to look at the surface plots. And we'll look first over the upper west, over Madison. Here we are, 39 over 36 with a light southerly wind, 10 miles visibility. And if you look at these maps I looked a little bit earlier today, only a few places near Cleveland, Akron area, Canton Airport, 39 over 31 with light snow reported there. But again, the precipitation band that we saw over Ohio was generally light precipitation, some of it just light precipitation. Not much going on to the north, over northern Michigan. You can see a little bit of light snow as well, 37 over 26. But it's really awfully quiet at this point. Let's go to the south a little bit, over Texas, where we saw that rainfall. Light rain, I don't think that's Austin, but 68 over 66, so a pretty mild day in central Texas. Where they have a lot of clouds, the temperatures are suppressed a little bit, but where it's a little bit clearer, it's warmed up nicely. So the impact of cloud cover is pretty evident in this particular picture. And over the Florida Peninsula, again, dew points in the 50s, which is not bad at all, and temperatures have already gotten up to the mid-70s, middle upper 70s. So just a really fantastic day over here. Let's go to western Canada. Okay, we're near our forecast station. Here's our forecast station. 33 over 31 with light snow. Again, this is just something exciting going on today. Sorry, it's just a quiet day.
Cold in Alaska, holy cow, minus 42, minus 33.
This is something we're going to watch. The really
Minus
chilly areas
47.
over northwestern Canada and Alaska, down minus 40 degrees Celsius or Fahrenheit in some places, in excess of that.
How's that
Really
looking
cool
at
there.
850 now? I'm wondering, now that we have that intersection occurring up there with the polar night jet and subtropical jet, I would expect that cold air is going to start appearing at 850.
Right.
It's going to lift it.
So we'll take a look at 850 in just a moment, and we also have Professor John Martin's diagnosis, which is looking at the area enclosed by the minus 5 degree 850 contour, minus 5 degree 850, minus 5 degree Celsius isotherm at 850 hectopascals, and that's a measure of just how cold it is over the hemisphere, and we'll see that. Actually, let's bring that up right now, and then we'll look at the upper air vents. Next would go. So again, this is the aerial extent of the minus 5 degrees Celsius at 850 on that isotherm in billions of kilometers. And what we can see here is this was just sent, this is fresh right off the presses. This is right now, that red line is the current trajectory, then he has averages over different periods. So you can see they're all pretty closely clustered with the extremes here. And so far, we're at the 15th warmest point in this plot over the last, I guess since 1948, the 15th warmest winter so far, or season so far. He starts this in early September. Again, the smaller the area, the warmer the hemisphere in general. And so you can see it's been climbing up, but it's never gotten much above the climatological average. So we're kind of right in the middle there. Not certainly the warmest, but not by no means the coolest. So, and this will continue all the way into February as he develops this particular chart. But that's a global measure. We're going to then look at some regional measures. So let's go to the 850 hectopascal superheat maps. And a couple things to note here. We have a broadly confluent flow here in the eastern half of the United States. And with that confluence with the baroclinic zone here, this is weekly frontogenetical, at least at 12Z this morning. And if it's sufficiently moist, like it is over northern parts of Ohio, not the southern region, you can imagine with this confluence, you get a Soyer-Eliason type circulation that's going to set up with that air rising. If it rises far enough up, it'll condense, form cloudiness, and maybe light precipitation. We have a trough axis that was just to our east this morning, or to our west this morning, and we saw the warm advection occurring, but it looks like the next surge of cooler air is just to our northwest. But again, a broad ridge protecting much of the southeastern part of the United States, and that's keeping them warm for a while. We're noting the really cold air over Alaska and western Canada. You can see minus 33 degrees, minus 33.2 degrees right over British Columbia and Alberta. And this is really cold air. I haven't looked at the time sequence of this building up. But again, this is probably some of the coldest air we've seen so far this season over parts of Canada and Alaska at this point. Maybe we could actually go back to your loops and take a quick look at how that's emerged.
There's a couple of missing frames in here.
Let's go to, I'd like to go backwards, but let's just start at this point, beyond the last missing frame, hopefully. So, the 28th on Sunday. Step back and look at numbers here. Minus 35.9 over to the interior parts of Alaska. And we just step forward a little bit. This is the easiest to make up the numbers, minus 31. So it's not super cold, minus 24, minus 21. So the air hasn't been initially, at least earlier this week on the 29th, which was Monday, wasn't super cold then. Let's go ahead a few days, please. The cyclone's going by, minus 28.6, minus 25, minus 24. Again, not cold, So something's happened over the last couple of days that's actually increased or decreased the temperature significantly over eastern Alaska and western British Columbia. This is going to minus 22, minus 26 degrees Celsius. Yeah, this isn't super cold.
It's the intersection with the subtropical jet.
Right.
It's doing it.
But I guess the mechanism that's causing that air to rise from 850 and above to cool it adiabatically, now you get these really chilly temperatures. Well, that's this morning, minus 35.2. If we go back a quick time-wise, minus 37, and back again. There's still minus 35 here. This is on yesterday morning.
I wonder if there's some terrain in that area that's kind of weird. The analysis just looks a little weird.
Yeah. What Pete's pointing out is you can see how these tight gradients are. This could be part of the Canadian Rockies up in here that are causing some distortion of.
Could be at the surface at 850.
Yeah, right. So if we go back one more quick, when did it get below minus 30? So you're minus 31, and one more quick back, minus 33. So, not a broad area of really cold air, and then it warms up a lot. So sometime on Tuesday into Wednesday, it really began to cool off up there in Canada. And so one of the big questions is that air going to eventually make it down to the lower 48? And we'll see that in the forecast. Not quite. Okay, let's go now to 500 hectopascal. So 500. I think one of the most conspicuous features we'll see here and some of the other forecasts is this really strong, nearly zonal jet that crosses much of the United States. Okay, maybe broadly confluent in the central part of the United States at 500 hectopascal out from southern Missouri all the way out to North Carolina. But really nice jet, and the fact that we have evidently cold air to the north over central Canada and relatively mild air to the south, that temperature gradient oriented along the same direction, or oriented to the south of the isotherms, basically in the same direction as the geopotential height contours here, indicates we're going to get a really strong jet right across the northern tier of the United States as we go up in the atmosphere. So we'll see that emerging as well. At 500 hectopascal, minus 43 degrees Celsius, up there for northern British Columbia, we get pretty chilly air out there. And we can see some of the, just off the edge of this, Hawaii's down here. You can see that really cold upper low that's located over the Central Pacific. Let's go to 300 hectopascal. And there's our strong jet, as we anticipated, from thermal wind. Right, we have the thermal wind vector basically oriented from west to east, along with the 5 millibar heights. That's going to add up to a stronger jet right across the United States, 157 knots over North Dakota. It's a pretty impressive jet. And there's still a little bit of a temperature gradient, so it might increase a little bit more as we go further to the north. Minus 60 degrees Celsius, minus 59 degrees Celsius down here in the minus 40s. So there's still a temperature gradient. We haven't quite reached the maximum in the jet location. You get the questions or comments, please ask. And we'll go up to 200 hectopascal to finish this one. And once we reach this level, you can see the reversal in the temperature gradient as we talked about in 452 and 751. So we're now in the lower stratosphere at this level. Minus 50 degrees to the north here in Hudson Bay, and then in parts of Texas, minus 50, or Kansas, minus 58 degrees Celsius down there. So we've reversed that temperature gradient. The jet's beginning to weaken with altitude above 300 hectopascal. So we just passed through. And you can see the isotherms here from temperature gradient, but now reversed. It's directed forward as opposed to equator. All right. But again, no obvious significant short waves in the flow at this point. And we'll just see how this is going to evolve over time for the weather for this upcoming weekend. So let's quit out of this and go on to the tab for Sol. You go up to the top. That's going to be right here. So we kind of do another current run and kind of do the usual. Look at the meteorograms. For us, we saw that trough that was at 850 hectopascal. We're still in sort of a warm advection region. It was going to head east. We'll get the cold advection. You can see the temperatures falling overnight tonight, as you'd expect, but then not really recovering tomorrow or on Sunday. Dew points also dropping. And the model is hinting at least some light precipitation, particularly as we get towards Sunday morning, so we're going to be curious what's generating. Let's look at a time height section. And on the time height section, you can see, again, yellow are isotropes. Red is the relative humidity above 70%, 70, 80, 90%, depending on the surface. You can see the winds as a function of height. Time runs from left to right on this particular map. And the dashed lines are subsidence, so here's the last bit of upward motion we had this morning. Here's some dashed lines here indicating that broadly subsidence that's occurring. And you can see the northwesterly winds, in fact, that are maybe transporting some of that colder air over us. And then by the time we get to late tomorrow evening and on Sunday, the winds go from westerly to easterly, so that kind of indicates a change in the pressure distribution over us with higher pressure toward north, this is the lower pressure toward south perhaps. But you can also see the winds varying with height, so that's going to be indicative of warm advection occurring and significant upward motion that's occurring. We're not quite moist enough yet until we get to the very end of the period when we have strong southerly winds and temperatures are beginning to get a bit milder. So that precipitation result is going to be accompanied with warm advection. One of the big questions is, where's the main forcing going to be? Where's the significant upward motion going to be? We're going to be cold enough for frozen precipitation, but will we actually get any here? So let's now turn to the surface maps. Look at that. We'll start at 6 hours in the forecast. And what the model is showing is some of that light snow we saw in Ohio moving into parts of Pennsylvania, east of Erie, and then, perhaps just very light snow or light precipitation expected along this baroclinic zone from North Dakota just to our northeast. And again, we didn't see much on the radar occurring there. I don't think this is probably going to really verify.
There were some reports of light snow to our northeast, like Beaver Dam, Fond du Lac, that were like could happen into an inch on their own.
No, but right now, falling.
Not right
This
now,
morning,
no.
right. Yeah, the stuff from this
no,
morning is already
right.
moved out.
Okay.
This is on the ground as of 18
I
days.
was thinking that was a few days ago.
Yeah, this is accumulating. Yeah, this is
Oh,
accumulating.
yeah, it was earlier this morning that I saw the reports.
All right, so let's go ahead to midnight tonight, 18 hours of forecast. And again, still forecast for light snow, but you'll notice that the key thing here is our winds now shifting to the northwest. Cold advection has begun. There's a little bit of light precipitation in in southern Tennessee, all the way across Arkansas. But again, this is a fairly quiet, tame pattern at this point. But the cold advection, that's going to herald some of the cooler temperatures we're going to expect for tomorrow. Nice intense cyclone approaching the west coast of the United States as well. We'll watch that. Let's go ahead to tomorrow morning, please. Tomorrow afternoon. So here's the cold air in with a nice anticyclone. We saw the subsidence occurring over us, so maybe we'll see a little bit more sun tomorrow than we're seeing today. And the next weather system is what was just off the west coast is now moved inland over parts of eastern Montana, or western Montana, excuse me. And we're going to see that this is going to be the main weather maker as it moves eastward over the weekend, but passing, by all accounts, toward north, so that's where most of the precipitation is going to be. This cyclone that's in southwestern Ontario is deepened a little bit. You can see strong cold advection occurring, and perhaps there's going to be some lake effect snows that set up over Lake Michigan and Lake Erie later this weekend. Let's go ahead another 12 hours to tomorrow midnight on Sunday, or Sunday morning early. That cyclone is, it was over Ontario, that's now moved into eastern Ontario near southern Quebec. And here is this fairly vigorous area of the cyclonic circulation, really strong warm advection. We can do some diagnostics of what are some of the forcing mechanisms for the vertical motion here. But some of this we will see as chronogenesis, but really a vigorous area of precipitation. Looking at about a half inch of liquid precipitation, or nearly half an inch of liquid precipitation over North Dakota. And the question is, how will this cyclone track over time, and what's the influence going to be over Wisconsin? We go ahead just 6 hours, so Sunday morning. slowly moving east-southeastward. According to this model, we want to look at a lot of them. Most of the precipitation is going to be north of us, okay? But it's all going to, this is most certainly all going to be snow from parts of northern Minnesota into the northern part of our state. We're going to be in warm advection at the 540 line, just right over us, but we know our surface temperatures are cold. Aloft is going to be pretty cold. This is not going to be, but it's too dry for us to get much snow precipitation by Sunday morning. Let's go ahead another, just 6 hours. And that 540 line moves northward, so this would suggest we might warm up a little bit on Sunday. But again, significant snow maybe in the northern part of our state as the cyclone intensifies and moves slowly toward the east. Nice cold front beginning to develop associated with the weather system. The thickness gradient is still back up over South Dakota and Nebraska with a nice surface trough that extends to its south. Watch how that evolves over time. But to look at this particular time, you can see significant warm advection. You can also see a hint at maybe an upper trough that's to its east. Let's look at this map time, 54 hours at 500 hectopascal, 850 first, then 500. Identify two things. So 850, really strong localized warm advection in this region with these southerly winds. Pretty significant cold advection out to the east of this. Right, so localized warm advection is one factor in the classic omega equation. Let's look next at the vorticity advection. Again, we'd like ideally to have a map of geostrophic vorticity advection, but there is a modest amount that's located downstream of this particular wave over parts of Minnesota and the northern part of our state. So not quite all over in the same location. But if you recall where the surface cyclone was, this vorticity advection back here is increasing with height. So this is going to be a region where we might see it's favorable for us. Let's look at the Q vectors at this time. So that's going to be down a little bit at 54 hours. Q vector convergence is maximized back over Minnesota, close to where we're downstream of the upper trough, as well as another maximum that's located just over eastern Lake Superior and northern Lake Michigan. So that's where all the action's going to be for vertical, we might anticipate for vertical motion. This is a map, not of omega. This is a map of Q vector convergence. It's a quasi-geostrophic diagnostic. And we're going to see a couple ways to view this in just a moment. The other interesting thing to note is that these Q vectors are aligned parallel to the isotherms here. Right? And since the Q vector represents the time rate of change of the horizontal temperature gradient, which is oriented like this, right? From the gradient's a vector that points in the direction of most rapid increase. If the Q vector is pointed in this direction, that's going to indicate that these isotherms are going to be rotating this way, which indicates the amplification of this thermal ridge over time. Likewise, to the east of the thermal ridge axis, you see these Q vectors are both along and across the isotherms, but generally pointing toward the east. So that's going to mean that these isotherms are going to be rotating in this direction as well. So this amplification of this warm thermal ridge is indicated. The fact that we have Q vectors pointing across these isotherms is a diagnostic of frontogenesis, particularly over the northeastern part of our state. Let's look at omega. And the Q vector divergence obviously is substance. This should be obviously. So omega is, just goes in. So between all of these areas, we looked at just one layer in the atmosphere. Again, northern Minnesota, we're seeing very strong vertical motions, as well as vertical motions over the northern and northeastern half of our state, over parts of Lake Superior and the upper peninsula of Michigan in that region. And strong, where we saw the Q vector divergence, some evidence of subsidence back over to South Dakota. Okay, and let's go ahead one more time to 60 hours at the surface. Cyclone, so where we have those vigorous vertical motions, you're going to see it was sufficiently moist for them to get precipitation, accumulated precipitation in the southern part of our state. As this now developing cold front that begins to approach our area, still southerly winds, but that's a possibility for us to get some precipitation. That's what we saw in a forecast meteorogram suggesting some light precipitation. But that cold air that we saw left over Canada is now finally gotten unleashed and it's now going to come in right behind the system. So the early part of next week looks like it's going to be super cold. One of the things that I want to point out, we looked at this diagnostic for vertical motion. I'm going to switch gears for a second and use the document cam, although I'm not going to use the document. So in 751, the graduate class, what we've been looking at is this classical omega equation, where omega indicates that is the vertical motion that we're solving for. We've been talking about this divergence of Q. There's our minus sign in front of it, so where we see Q vector convergence, that's seen as a diagnostic for vertical motion. Again, the Q here represents the time rate of change of the potential temperature gradient following the geostrophic motion. S is a measure of the stratification. This Laplacian here is just the two-dimensional horizontal Laplacian. This is our second derivative in the vertical. So we have an equation that looks like the second derivative of some three-dimensional second derivative of some variable omega, which is the vertical motion, is proportional to, or has this sign. What is the sign that we're looking at where we have upward vertical motion? If there's Q vector convergence, this is negative, this is negative, this is positive. So we have a positive second derivative. Omega, what we're solving for, has a second derivative which is positive. If the second derivative of a function is positive, that means locally it's going to be a minimum. If we solve this with omega equals 0 on the boundaries, that means omega is going to have to be negative in the interior where we're solving this. So let's go to the Jupyter Hub server. We're going to look at a particular time. This is actually 72 hours in the forecast. And we'll look at an example of this calculation for this same cyclone event, but as it gets a little bit more wrapped up to our east. Oh, great.
See if you change the.
Great. Okay. Well, I'm not going to see this. Use the server, something weird going on this morning. Okay. We can, it's going to take a while to run, so I'm not hang on. Let's go to the pivotal. I'll show this next one. Go to models, we'll go to 72 hours. Cyclone's wrapping up nicely. Nice cold front that's developed along this cyclone. Remember we saw the low moving across just to our north. This is Monday morning. This is going to be some of the coldest air of the season coming out. Had a nice diagnostic of the vertical motion along the cold front, as well as the vertical motion on the northern part of this system, but unfortunately something that didn't quite come together in the solver this morning. But we'll take a look at temperatures here. Let's go to the 2-meter temperature and wind speed. Up above, right there. We can hover over the near Madison. So in front on Monday morning, low 20s with strong cold advection. The wind chill index at that time, which combines the effects of wind and the low temperatures, it's going to feel like it's in the single digits above 0 Fahrenheit when we arrive. But as Greg was pointing out, that really cold air that was over parts of Alaska, British Columbia, and Alberta has now been unleashed. And it's interesting, it's right in the area that Greg was suggesting where you see this confluence of both the subtropical jet coming underneath the polar night jet. Very often these intersections spawn the development of significant cold air outbreaks. This may be where this is the origins of this particular outbreak. At least it's consistent with what Greg's been saying. So really cold weather coming in. I think this is consistent across the forecast over the last couple of days. Let's go ahead to 96 hours. Let's go back to the surface map, please. Actually, I want to do one. Okay, so the surface map indicates another cyclone developing to our southeast. Let's go back to 48 hours just to verify that Sunday morning situation. Yeah, the GFS also has most of the precipitation of snow to our north. In fact, it's in the northern half of our state instead of the northern 2/3 of the state. So this cyclone is not going to be super impactful for us.
Can we look at maybe 2 other forecast times to see how consistent they're?
Yeah, let's do that. So we can go back to, let's go back to the 6Z run. And then to 0Z. So what Greg's question there is really a good one. When you're making a forecast, you don't want to take one model run. We looked at GFS, we looked at the GFS from Colsey today. We also looked at the MM5 from Colsey today. But you also want to look at runs from earlier because the data that goes into those models can have a big impact on what the forecast is doing. And in many of these cases, in all of these cases at least, it seems to be keeping most of the precipitation well to our north. So that's something that's interesting. The structure of it, you can see, has changed as the models have developed. If we go back to the most recent forecast, you'll see that this low is a little bit better defined, and the one to its south is also a bit better defined. So a much stronger cyclone system approaching us from the west. We saw it 96 hours. We'll go back to 96 now, just looking at the week ahead, weather-wise. Cold air is in. We have another pattern of strong warm advection that's beginning to set up over the southern plains. Let's just step ahead in 24-hour chunks. We'll go to 100. Yeah, let's go to 120. That's a little bit big. It's too fast. We'll go to 108 in this. So 12 hours after that, this looks like Tuesday night. We have a period of light snow over us as that weather system goes by. And then by the time we get to Wednesday morning, that's headed out to the east. And nice cold high to the north, but this is moving pretty rapidly. There's not much evidence of what's called, well, there's a little bit right here. So this is kind of a neat thing. This is cold air damming, the cold air trapped up against the Appalachians. We've talked about this a little bit in one of the papers we were reading in 452. Right, you can see this, see how the isobars are kind of kinked in this region. Here's where the Appalachians are. So this cold air gets trapped to the east of the Appalachians. This isn't the best example of cold air damming, but as the air heads southward, it gets turned to the right by the Coriolis force. It gets parked up against the Appalachians, and it's just kind of surging southward along the east side of the Appalachians. And that can lead to ice storm conditions in some situations when you have a cold air heading southward, but you have above that warm, moist air that's being evected northward at higher levels. If the cold air is trapped here, you can get freezing rain situations, which is kind of what you're seeing right here.
At the lower levels, you're getting an upslope over the dam.
Right.
Over the dammed up air.
So we could actually look at the temperature and winds at the same time. And I think we'll see a little bit, see the evidence of it. So here's that cold air. Again, the Appalachians are right about here. The spine of the Appalachians right about here. And some of this cold air is trapped here. Some of this is just cold air on top of the Appalachians. But you can see how the winds, really strong winds off the east, out of the east, and then they get really light in this region right here. This is not, again, the best example, because we would expect to see strong northerly winds, kind of like what you see at the southern edge of this over near Raleigh, North Carolina. But that cold air gets trapped there, and you can get what's called a coastal front development.
But the reason the winds are getting light too is that the winds from the east are not going through there, they're rising at that point, going up over the cold air bubble.
Right, so you have this warm advection out over the ocean. Cold air is trapped here, so what happens is the air is forced to rise up over it. And so you get this near stagnant area underneath this.
That effectively extends the effect of the mountains
To the
eastward.
east, yeah. So your mountains appear to the model, appear to the atmosphere physically further east than up here. Let's go ahead another maybe 12 hours. I think this will get washed out, but yeah, that warmth. Once you get a cyclone developing, you get westerly flow, we get downslope, begins to mix all this out, and things head out to the east. You don't see much evidence, or any evidence really left over for cold air damming when you get that developing. And over us, again, this is already a couple days past, just broad cyclonic circulation over us.
But I think what's going on over the Berkshires is cold air damming again.
It's still stuck here, right? So the cold air damming is still occurring north of the cyclone center, to the southwest of it, with, kind of weak winds. That westerly wind and downslope over the Appalachians kind of breaks this up. So the cold air then is evident there. But you can see, again, this really significant tongue of really cold air, hydrostatically shown because of the fact that we have this nose of higher pressures right to the north of this. If we go back to the temperatures at this time, you'll see that cold air is really trapped up within the lake mountains.
This is $1 million snow for the ski areas of New England.
But this time of year, if it can stay cold beyond this time period.
Yeah, as long as that cold air is parked up there and upsloping over, it looks like most of it is, so that at least from about mid-Vermont northward, they're gonna be all snow. I'm not sure about Stratton and the southern ski areas, but it's close. They might, and sometimes on these things, they'll get 48, 72 inches of snow with a system like this.
It was a pretty good setup for northern New England snowfall, but here, the influence of the ocean, it's still pretty mild. Ocean temperatures are probably still 40s and 50s. That east wind is going to erode most of the cold air until you get to Worcester or further west. All right, so let's go back to the surface map, and we'll jump to 144 hours and then get to just next end of the week. And then call it a day. But cyclone moves out, and we're now in a situation with, again, more advection starting up, but it's relatively dry, so you're not seeing much in the way of precipitation. This isn't a particularly cold period at this point on Thursday, and we'll just go ahead to Friday of next week. We're still, but this weather system quickly moves by, and we're back into cold advection again for next weekend. But I'm curious. Let's go ahead, one more 12-hour period, so let's see what happens out of the southwest here. We may be talking about another snow event next week, but I haven't looked at this enough to say anything substantive.
That's a good Denver snow situation then.
Over here.
Yeah.
And another kind of cold air damming type
Right,
structure, right?
it's cold air down.
See the cold air? Hydrostatically reflected in this kind of nose of really higher pressures here, Rocky Mountains here, getting this, as air just travels southward.
So normally Denver's on on a very gentle slope of the high plains, and then to the west of Denver, you see the mountains.
Right.
And so much of the snow is often confined to where the mountains actually are. This extends the effect of the mountains onto the plains, and so Denver can get pounded by snow, and you get this kind of cold air damage.
Right, so if you didn't have the cold air here, the mountains are right here, and so basically air hits the mountains, rises, and produces the snow right here. Once the cold air gets trapped east of the mountains, you basically have a sloping, I mean, this always slopes upward, but this slope gets really steep here, and so you can then extend the effect of the mountains eastward and get snow in this region where the cold air is down. That's what we're seeing there. Okay, that looks good for later on, but let's wait until hopefully next week we'll see this, our last weather watch of the year, we'll see that. We can actually go back to the 0-0 run to see if that looks.
Maybe 2-hour forecast for this coming Wednesday had a pretty good snowstorm. I remember you coming in and telling me, oh, 11 inches. It's
Yeah.
gone.
From this, okay.
Yeah, no, that was from a couple days
So
ago.
let's go to the 0Z run. There's something there, it's a little bit colder. Right? This is more ice than snow.
Warmer for us, right?
Yeah, I mean, sorry, a little warmer, but it's current run is a little colder. If you go back to earlier runs, nothing. So don't get too excited, hold your horses on that. I'm just curious if that Jupyter notebook thing ever finished or was it?
I don't think it's running, I think it's
Something's on. All right. Well, I'll show that next time. What I wanted to show with that is you can look at Q vectors from now to the end of time. You can look at their convergence. But unless you do that numerical solution, some of the places where you see the convergence, not much is happening because of stratification issues. You have to really look over a great depth.
Which kernel were you running?
I think it was just the Python 3. But in any case, I'll show this next week and just show the solution. But this one really matched up nicely with the actual vertical velocities. That's about it for today, unless there's something else folks want to see. Yes?
So how much snow can we expect to accumulate this weekend in places like Minnesota and North Dakota?
Okay.
From that low pressure system?
That's moving back, right, it's moving across. I think the amounts in this are probably gonna be in the 4 to 8 inch range over the northern part of the state, but we can bring that up. Let's go back to total accumulated snowfall, and maybe just do regional. That done right there, Midwest. And then look at snowfall at the bottom, winter weather. Just the 10 to 1 ratio. Total? Yeah. And go to 60 hours. So the purple on the legend right here, you got 6 inches, is going to be this purple area. It's in fully far northern Minnesota and just east of Lake Superior. that might be actually lake enhanced. The northern part of our state looks like sort of 4 to 6 inches in the northeastern part of the state. And again, we can do this. Gee, if we could go to the man as well. That's less generous. With these snowfall, that's only a couple inches or so. But it's definitely, I think, actually, they definitely appeared cold enough for snowfall to accumulate up there, so this seems like it's a little bit on the low end. And lastly, if we could just look at the east WF, we can get that, hopefully. Sorry, the other one, the high res. It's not good. I have to log on to my account to get that for the snowfall. It's not gonna show up on this. Oh, there it is. Okay, there we go.
Maybe not.
We can't zoom in on it.
You're not
This is through
at 60
48 hours. Let's go to 60 hours. Or 72. 60 hours. Yeah, there's some places to get about 6 inches, but maybe this looks like more 2 to 4 if you look average the models. Well,
Quick shout out to some people watching online. James Hughes had some input earlier. He was interested in John's cold weather, or cold air dome plot. He cuts 11s. Is on the call today. She says they're expecting some pretty good lake enhancement along the north shore of Lake Superior.
right, so, yeah, Kensel Evans graduated a couple years ago from our program. This is the area that, she's a forecaster in the Duluth?
I think so, yeah.
Okay. And so they're looking at this area right here with an east wind. That cyclone call is going to track to the south. That east wind off the Lake Superior is going to create some significant.
There's a pretty steep topography there in the North Shore.
Yeah, and that's another good point.
It's about almost, what is it, 1,000 feet or 1,500 feet
Great.
in places.
And Jim Hughes, or Jim Bob, as he was sometimes affectionately referred to, he was a graduate about 15 years ago or so from our program. So hi to those folks and anyone else that's joined us today. But this will be our next to last weather watch. Our last weather watch will be on Friday next week. Hopefully we'll have some signs of a neat snowstorm for the next week. So the models right now are a little bit indecisive on that matter. But thanks, Greg, for sort of a quick review of what's going on with the status of our change in seasons and the interaction of the jets. And we'll see if that colder outbreak does actually, in fact, make it down to our latitudes, because Sunday night into Monday morning it's going to get really cold and really windy. So it'll feel like winter early next week. Thanks, Pete. I'm glad you clicked on this.
I was looking for something else before we go here.
Yeah. One last thing. So we run the MM5. We've been doing this for years. This was set up almost 20 years ago by a student, former student Darrell Price. And one of the things I happened to come upon is we keep track of the forecast errors in the model. So this way this is read, we have the model runs from earlier this week, in the last 60 hours or so. So the forecast valid. These are analyses, and then these are the errors associated with forecast valid at this time. So the older forecast valid at this time, and the forecast errors associated with them are plotted here. So if you were to go to, as an example, this is the error associated with a run from 24 hours ago. Shows the forecast error in geopotential heights over the western part of the United States at 500 hectopascal from this 24-hour forecast. Right? If we go back to that tab and look at forecast valid at the same time but shorter run length, this is a 12-hour forecast. You can see you would expect forecast error should decrease as the run length gets shorter. But let's go ahead in time a little bit longer, so longer forecast length. Now here at 36-hour forecast errors for zero is not going to count. Go back a second, please. 24 hours. Okay, so these are forecast errors for model run from 24 hours ago. This is a 24-hour forecast hour for a model run that was initialized on 0Z the second, I think, right? 0Z on the second. No, it's valid 0Z on the second.
What's the resolution?
This is a 90-kilometer run. It was a 90-kilometer run. So if we go back quick, I'm trying to, should have better looked at this. If we look at a shorter term forecast, when it's 12, let's go longer, 48 hours under the same heading. It's still blank. Sorry, Pete, one more. If this doesn't work, some of the runs ran, some of them didn't. And these aren't the same maps I was looking at earlier. So The idea is you can keep track of forecast errors over time and look at how the forecast error, the consistency of forecast errors from one run to the next time. I'll better describe this in the next meeting. The other interesting aspect of this is you can then take these forecast errors, run what we call the adjoint model, backward in time with some sort of measure of the forecast errors, U, V, T, and figure out what are the origins of these forecast errors. And in some situations you see very similar forecast error structure, in other cases you don't, but you can build up a climatology of, when you see forecast errors here are the places where data would have been helpful to alleviate the forecast error. But I'll explain this setup better next time. I'm rushing through this, and I'll just end at this point. So thanks Pete, thanks Greg, thanks everyone for attending. If you have any questions, be around for a little bit afterwards since we're finishing up. Thanks again. This actually stays up here. Look at that.
Do you compare the forecast errors with the forecast GFS?
Yeah, so we use the analysis, whatever the analysis is used for that run.
Well, I mean, GFS made forecast errors too.
Oh, yeah, we haven't done that. We haven't done that.
Because your errors are very GFS in your model,
Right.
not.
That's fair.